Hello everybody, and welcome to my presentation on how the biogeochemical variability of coral reefs can be modulated by physical processes. As we all know, the chemistry of the oceans is changing. The surface pH has declined by about 0.1 unit over the past 100 years and may decline by as much as 0.4 units by 2100. Similarly, the ocean has lost around 1% of its oxygen over the past century, and by the end of this century may have lost a further 3 to 4%. Both acidification and deoxygenation have been linked to negative impacts on coral reefs, with acidification being found to increase the severity and delay the recovery from thermally induced mass bleaching events, while low oxygen events have recently been linked to coral mortality, such as this example here from the Flower Garden Banks National Marine Sanctuary. So we know the oceans are changing, and we know that these changes will negatively impact coral reefs. However, predicting how they'll impact individual reefs is still difficult for a number of reasons. One of which is coral reefs are highly variable environments. While the open ocean pH has declined by about 0.1 unit over the past century, some reefs, such as Hog Reef here in Bermuda, experience swings in excess of this just over a day-night cycle. Similarly, Hog Reef experiences large swings in dissolved oxygen, and Hog Reef is far from the most variable reef out there. So if we want to predict how changes in the open ocean are going to impact individual reefs, we need to understand what drives this variability. As we might expect from the classic diurnal cycle we see in pH and oxygen on coral reefs, a lot of these changes are driven by biological factors, such as photosynthesis or respiration. However, these biological factors are in turn affected by physical factors. For example, the photosynthetic rate of corals increases with increasing light intensity, at least up until a point. In addition to light, reef-scale hydrodynamics also play an important role in controlling coral reef biogeochemical variability. These are two drifters that were released from the same point on a reef, Japan, but on different days, and as you can see, they behave quite differently. The drifter in white leaves the reef system in about 3 hours, while the drifter that followed the orange path took over 7 hours to leave the reef system. All else being equal, we'd expect to see much larger biogeochemical changes on water that followed the orange path than the white path, just because it spent more time in the reef system. And so to a first order, we can approximate this by saying that at faster flow speeds, we expect to see smaller pH or oxygen changes because the water spends less time on the reef. And so we can say that the change in pH or oxygen is inversely proportional to flow speed. So given that, we set out in this study to try and answer the question, how much influence do light intensity and flow speed have on coral reef biogeochemical variability? We conducted our study on a reef on the western coast of Okinawa, Japan. And on a reef's a fringing reef system on which we put out a number of different instruments. So these circles here represent current meters. We put out pressure sensors on the forereef. And then at these 3 yellow stations here, which I'll be referring to as the reef flat, the lagoon, and the channel, we also measured biogeochemical parameters. So we also measured dissolved oxygen and pH. On the reef flat, we also measured photosynthetically active radiation, or PAR, which we use for light. Later on, I'll also be talking about waves and the circulation of this reef, and we measured waves on the forereef at this site here using an ADCP. So we left the instruments out on the reef for about 3 weeks, and this is what we found. On the top panel here, we have the pH, then the dissolved oxygen, the PAR, or photosynthetically active radiation, and then a tidally filtered flow speed. So this is the flow speed at the 3 sites, but with the tidal signal removed. And if we look at this, one of the things that immediately jumps out is that we see that classic diurnal cycle with pH and oxygen peaks during the day and troughs at night. But if we look across these time series, we see that the magnitude of these peaks and troughs is not consistent. For example, if we look at between October 17th and October 20th, we see declines in the maximum pH and oxygen values, and these declines coincide with decreasing light intensity across this period, suggesting that light does indeed play a role. It's clearly not the whole story, however, as the day before we see peaks in both pH and oxygen, despite the light intensity being lower than it's been for the preceding week. However, on this day, we had slower flow speeds than we'd had for the preceding week, suggesting that flow speed also plays a role. To dive into this further, we calculated the mean flow speed for each day, the mean light intensity for each day, and then the maximum deviation from the time series mean for both pH and oxygen for each day and each night. So, for example, we took the maximum pH on October 16th and subtracted the mean pH value for the entire time series. We then regressed those differences against the mean speed and against the mean light intensity. So each dot here represents a day. The x-axis is the inverse mean speed. Remember, we expect to see larger changes at higher inverse mean speeds or lower flow speeds. And the colors here represent the daily mean power intensity. So for dots of the same color, we expect to see a trend in this direction. So days with the same light intensity, we expect to see larger differences on days with slower speeds or higher inverse mean speeds. And we expect to see a color gradient in this direction with larger changes on days with more light than low light if the speed's the same. And that's really what we see, particularly in the lagoon, where these two factors alone account for about 3/4 of the observed variability. They account for about 60% of the variability on the reef flat and just around 1/4 in the channel. If we run the same analysis with oxygen, we see similar results, with around 70% of the variability explained by these two factors in the reef flat and the channel, and around 1/3 in the lagoon, though it should be noted that our lagoon oxygen sensor became biofouled, and so we just don't have as many points from this area. At night, there's no light, so we can simply regress the change in pH, or the change in oxygen, against the inverse mean speed. And again, we have pretty good agreement everywhere except the channel pH, with these fits explaining between 58 to 78% of the observed variability. The keen-eyed among you may notice that these fits are probably strongly influenced by these distant points out here. But if we rerun the analyses without those points, the lines that we get, or lines of best fit, don't differ markedly. So these dashed lines represent these lines run without these points, high leverage points shown as diamonds. So we found that light intensity and flow speed can explain a large proportion of the observed pH and oxygen variability, which really begs the question, can they be used to predict it? To investigate this further, we needed to constrain the circulation of the coral reef system. And so using this sensor on the full reef, we were able to measure the significant wave height, or the mean height of the tallest third of waves that were coming in. The flow speed in the lagoon, so this is now the full time series without the tidal component removed, and also the tide. And when we look at this, what we see is that the significant wave height is pretty well correlated with the flow speed in the lagoon. When we have peaks here, we have peaks here. When we have troughs here, we have troughs here. However, there's a lot more short-term variability in this speed time series, and if we zoom in closely on these sections, we realize that a lot of that occurs on tidal timescales, with low flow speeds at high tide and higher flow speeds at low tide. So using these relationships, we were able to develop a model for the flow speed based just off tide and significant wave height. And these predictions are shown in black here over the measured time series that are in color. Unfortunately, we weren't able to get a pressure sensor onto the fore reef at the start of the experiment, hence the lag here. But as you can see, these predicted flow speeds do a pretty good job of capturing at least the general trends, if not, every maximum and every minimum. Seeing this, we reran the same analysis we did before, except instead of using the measured mean flow speed, we now use the model mean flow speed. And again, we get good fits everywhere except the lagoon, where because our sensor became fouled late in the time series, and we couldn't get a sensor on the fore reef until midway through the time series, we only had about 3 points. But outside of that, these two factors alone, the modeled flow speed and the measured light intensity, accounted for between 53 and 92% of the observed variability. If we run it at night, the fits aren't quite as strong, but they still account for between 51 and 83% of the variability. So these results strongly suggest that it may be possible to predict coral reef biogeochemical variability from physical factors, at least on this reef under these conditions. And what's more, it may be possible to make these predictions using relatively few instruments. So our modeled speeds came from one pressure sensor, and the measured light intensity came from one power meter. However, what works on Honor might not necessarily work everywhere. For example, this is a rather complex reef from the Great Barrier Reef, and this is the Maldives. And so these two reef systems probably hydrodynamically behave very differently than what we saw at Honor. This doesn't mean that we can't predict the biogeochemical variability here. I think it just means that we need to develop a better understanding of what links the physical factors and the biogeochemistry. One way to do this would be to go conduct studies on all these reefs. However, there simply isn't enough money, people, or time to get this done. Luckily, there may be other ways to do that. Recent advances in shallow water bathymetry derived from satellites and the presence of global wind, wave, and tide models mean that it may be possible to develop numerical models of reefs over a much greater spatial scale than would be possible if we went out and conducted field experiments. Similarly, while I've been talking about the physics, the biology is really important for this variability. And so with the advent of things like the benthic maps found on the Allen Coral Atlas, it may be possible to fold those into these numerical models and predict biogeochemical variability that way. And that's something that I've started working on now. So these are very preliminary results that I won't get into, but if this is something that you're interested in or have some ideas about, I'd really appreciate talking to you. So we found that flow speed and light intensity can explain a large amount of the biogeochemical variability that we observed on this reef system. We also found that on this reef system, the flow speed is highly predictable from relatively simple measurements, and find that this strongly suggests that the biogeochemical variability on coral reefs may be predictable from similarly simple physical measurements. I'd like to thank my amazing co-authors, our funding sources, and Ariel and Travis for their photos. And I look forward to answering any of your questions.